Standard machine learning is a passive process designed to map patterns within a fixed dataset. This linear chart shows the flow of an ordinary model. It takes an input, runs it through a mathematical black box, and produces a prediction, often without understanding the physical mechanisms at play. Physical systems are governed by causal structures and conservation laws, rigid requirements that statistical correlation alone cannot satisfy. When you push a static model outside its training data, it fails. Physical reality collapses into unpredictable states that a simple pattern matcher cannot anticipate. Advancing physical research requires an architecture capable of active, goal-directed discovery. This requirement is met by the AI Physics Agent, an autonomous system built to execute the full scientific method. As shown on the right, the agent operates within a continuous four-stage loop. It observes a physical state, reasons through a model, predicts, and acts. The system physically tests its hypotheses, feeding new empirical evidence back through the observation step to update its plan. This artificial intelligence operates as an active participant in physical research. To understand how this loop functions, we must deconstruct the agent's decision-making engine. It begins with how the system represents its environment. The state, S sub t, represents all data and measurements the agent currently holds. This state feeds into the policy function, pi, calculating the probability of specific actions. These actions are driven by the J of pi formula, maximizing total expected usefulness. To maximize that usefulness efficiently, the engine must be strictly constrained by physical reality. High-level physical data is difficult to acquire. Gathering information from particle collisions or cryogenics is expensive, noisy, and sparse. Running these experiments requires immense resources. A model cannot afford to run thousands of failing trials just to identify a pattern. The solution is physics-informed AI. The loss function penalizes the model for violating physical laws, acting as rigid boundaries. If governed by the heat equation, that formula is built into the AI's architecture. These constraints restrict the neural network's predictive curve, preventing physically impossible states. By mathematically forcing the AI to obey the laws of physics, the agent learns accurately with significantly fewer real-world measurements. Once the model has a physically constrained hypothesis, the agent must decide which specific experiment to run next. The agent uses Bayesian updating to refine plausible parameters under uncertainty. To optimize search spaces, an acquisition function balances two competing drives. Exploitation tests parameters where predicted performance is high. Exploration pushes the agent to test where uncertainty is largest, guaranteeing new information. Balancing these two factors allows the agent to intelligently initiate physical synthesis in the real world. Combining the policy engine, physics constraints, and Bayesian optimization creates a self-driving lab. This flowchart shows the pipeline for discovering materials with high electrical conductivity. It begins by accessing historical data and training a model to predict new compositions. In step 3, the physics-informed architecture filters out compounds that are chemically unstable or thermodynamically impossible. The Bayesian optimizer then selects the single most informative target, triggering a robotic system to synthesize the material. Finally, the empirical results from that synthesis loop back to update the initial dataset. The scientific method iterates at machine speed. This architecture is already deployed in automated materials research facilities. As the deployment matrix shows, this infrastructure is explicitly designed for highly complex, high-dimensional, and noisy problems. It is important to clarify that these agents are not autonomous robot scientists that automatically discover absolute truth. As the reality check notes, explicit human feedback and expert judgment remain critical for interpreting significance and ensuring experimental safety. By automating research bottlenecks, AI physics agents transform the study of reality into a continuous, intelligent loop of action and correction.